Okay. Let's begin. Let's make... Alright. So, as I promised, today we will talk about at least breadth first search and depth first search. Probably in the reverse order, so let's... So let's do a little bit of review, just to talk about what we're talking about. So remember that in general, a graph, right, is a pair, VE, where V is a set of vertices. Basically, V is just a set of names. Yeah, we'll do a final exam review next class. Yeah, maybe I'll... Okay, yeah, I guess we'll do some announcements. Basically, I'll release the final exam probably the 14th. It'll be due the 21st. It'll be same format. I think I've said most of this before, but it doesn't matter. So our last class is next Tuesday. So I'll do a big review of everything. I think I'll also probably post, maybe I'll take one of the previous finals and post it on Discord so you can review it. Yep, I think that's basically all I got. Yeah, okay. Okay. Let's see. Okay, cool. So, I think that's all that I really need to say about that. So E is a set of edges, right? And edges are, remember, it's not all of the possible pairs, it's some of the pairs, x, y, such that x and y are in V, right? So V is basically just a bunch of names of vertices, right? So whatever you call them, if you call them ABC, if you call them x1, x2, x3, W1, V1, doesn't really matter, right? So you see a lot of different names for vertices, but it doesn't really matter what you call them as long as they have names. And so the edges are just some of the xy's. So remember that the difference between a directed graph and a directed graph and an undirected graph. So the difference is basically, in a directed graph, you can have situations like this, where you have, say, some circles, like this, and then I think we can actually draw them. If we're smart about how we draw this, we should not need to. We can just put a single arrow in, and then... So here's a little graph. Currently, we would say that this is an undirected graph because there's no arrows on it. But the thing that, let's make this into a directed graph. And let's just put an arrow on the end of all the... See, and that's why I wanted to be smart about it. So you see that, like for instance, if you have something that's starting at node A, right? In an undirected graph, there's no problem with node A. You can go to node whatever, say, B and C. Here's node C, here's node D, right? You can go around to all these different nodes. There's not really any problem. But here, when you have a directed graph, directed graph, you'll notice that there's paths from A, right? So for instance, like, if all the nodes have the same, like, the edges are equal to the set, well, AB is an edge, and AC is an edge, and I guess BD is an edge, and CD is an edge, right? And so those are all the edges in the directed graph. And so you see there's no way back to go back from, say, B to A or C to A, or right? So in an undirected graph, the difference is that here, if we have AB in the edges, we also have BA, right? And if we have AC, we also have CA. And if we have BD, we also have BB. And if we have CD, we also have DC. And that's what makes it undirected. What makes it undirected is that if XY is in the edges, then YX is in the edges. Okay? So, okay. So that's all the review about graph theory that I really want to do. It basically just, the important thing to realize about graphs is that they have vertices, they have edges, and that's it. So these are kind of complicated structures. The problem with them, right, especially if you're dealing with, like, with an undirected graph, is, let's say I try to traverse this thing like I do with, like, a binary search tree or something. So I say, well, first let's start at A. And then what I'm going to do is I'm going to say, okay, A's children, I'll call them children, I guess, just like pretending it's a tree, are B and C. So if we go to B, right, B's children are A, C, and D. So for instance, I don't know, so it depends on what you want to do. So if we're doing something, I guess if we do like a depth first type search, then the next child, the first child on the list of B's children is going to be A again, and the children are B and C, and then we go to B again, and then we get A, C, and D, right? And then etc. So we never actually reach C or D. So that's problem number one. We never reach C or D. Problem two, we never really terminate, right? So that's a big problem, right? So basically we have either an infinite loop or infinite recursion, and there's also nodes that we don't reach. So we go forever and we don't even get to everything. So one solution to this, if we wanted to traverse a graph, so if we're thinking about the graph traversal problem, which is really the graph search problem, right? So maybe I'll just call it the graph search problem, right? Because a traversal, if you don't have any rules, right? Like for a binary search tree, you have a bunch of rules that say if the thing is less, then you go left. If the thing is greater, then you go right. But the problem here is that there's no rules for greater, less. You just have to search everywhere, right? It'd be like if you had a tree, right? Let's just say you had some kind of binary tree. Of course, I'm going to be pedantic here and say this is a binary tree, but not a binary search tree, right? So this is not something that's going to satisfy the search tree property. And if we had something like this, and we just had some numbers in here, and I said, well, 5 is in here, 7 is in here, and 2 is in here, and 13 is in here. I'm almost making it a binary search tree, so let's not make it a binary search tree. 4 is in here, and 17 is in here, and 3, right? So it's like an anti-binary search tree. So the thing is, you don't have any idea, right? There's no rules anymore about where nodes are going to go. And so that's the question that we're dealing with graphs, is like if you start at 5 and you're trying to search for 3, now normally if this were a search tree, you would go left and then you would say, well, obviously this doesn't make sense and there's some problem here, but like if you found 4 here, then you would say, okay, now you're going to keep going that way and either get to 2 or 3 or something like that. So basically graphs, there's no rule. So this is basically like a binary tree without any rules, so it's not a search tree. well, I should say, without any like order rules. It has some structure rules in the sense that the structure is still binary, but anyway, so I think you get the point, right? So the structure is still binary, but it's not a binary search tree. So that's the problem with this graph business, is that you don't really know where you've gone, and it's possible to get back to the same place. So here's one solution that is always possible, right? And so generally, I think we've talked about this a little bit when we discussed well, I know I've discussed it in 201 before, but I'm not sure. We've definitely not discussed it in 341, but here's one solution that I'm going to offer for you. So you have a graph structure. One solution is possible, and let me show you. It's not the only solution, right? So let me get this graph, but it's definitely the easiest and the simplest and the kind of, I'm going to say, the most obvious solution, right? So how do we solve problem number 1, or never really terminate, because we see the same nodes over and over. So what we're going to do is we're going to make sure that one solution is always possible. We can mark nodes as visited, right? And so I don't care exactly what you mean by marking nodes as visited. Sometimes we'll make an auxiliary array. So the actual implementations of doing this are either say the node might have a visited variable in it that we can set them all to false and then set them to true as we go, or we can create an auxiliary data structure that keeps track of the things that we've visited, etc. Right? So the thing is that there's a lot of different things that we can do in order to implement this, but you notice that if you can mark nodes as visited and then you don't go, or if you get to a visited node, then you just don't, either you don't go to a visited node, or once you get to a visited node, you just don't keep going, right? So those are the two options, right? So you just stop when you get to one, right? So those are your two main options, and it's kind of basically the same code. It's like where you implement the edge case in your recursion. So let me show you, and here we're talking about depth first search mostly. So if we're going to do like a depth first search, let me explain what a depth first search is. The depth first search is the idea that, well, let's just do it and then I'll explain it. So you start at A, and so A has the children B, C. So basically what you do is you stick B and C onto a stack. So B and C go onto a stack, mark A, right? So now A is marked. So let's, mark A. I guess A gets marked with green. And now the question is, which one goes on the stack first? So let's assume that the stack looks like this. So the stack has B at the bottom and C right above it. And so the next thing we're going to do is we pop off the next thing off the stack, pop the stack, go to C, mark it, and push on B and D, right? And so here what we're going to do is we're going to take off C off the stack, and then here we're going to push B onto the stack again. So B was pushed on from A, but B was also pushed on from C, and then we're going to push on D. So we pop the stack in again. We go to D, mark D, and then we push B and C, right? And so the thing is that at this point, so we'll pop the stack, we go to D, we push B and C. So here's C, and then here's B again. So the stack is kind of looking weird. It's possible, so you can always fix it so that you're not pushing the same element multiple times if you mark them as visited and then don't. There's ways to fix this, but this is like the simplest possible case here, where you just have this stack, and so then in the end what you're going to do is you're going to say, okay, pop the stack again, go to C, but here C is marked, right? Don't do anything, right? And so then C gets popped off the stack. So actually I should mark C and D. The only one that hasn't been marked yet is B. And then we pop the stack again, right? One last time, pop the stack, one last time, go to B. Well, I mean, it's actually not the last time we can continue popping, but go to B, mark B, push. What are we going to push? We're going to push A, C, D, right? So technically we're going to get an A, C, and a D, or DCA. It doesn't really matter what order we're putting them onto the stack. But then what do you see? What you see is that for the rest of this, what's going to happen is that, well, you've already visited A, right? So the next time you pop off the stack, A is going to disappear. Next time you pop off the stack, C is going to disappear, then D is going to disappear since that's marked. And you have B 3 times, and all of those are going to get pretty much disappeared because they're all marked. So the algorithm that I've just done here, right, where basically what you do is you start with a stack, right? You push the starting element, then you pop an element, 3, mark that element as visited, right? 4, push the children. 5, go to 2, right? And really I should say there's like a 4A, push the children if not marked. 4B, quit, or I shouldn't say quit. I guess it's like a do nothing, right? Do nothing if marked. So don't push any more children on if it's marked. And so that's basic. And so what we've described here is the depth first search algorithm. This is DFS. Okay. So I think it's a pretty cool little algorithm. So what can depth first search do, and what can it not do? So here's an example of what it can do. It can search a graph, and of course here I don't even have an element that I'm searching for. I'm just I'm doing a traversal of the graph, really, is what I'm actually doing. But you can see that if I were searching for C, eventually this algorithm would stop. So basically, if you're doing a search, then you can always test, like, pop an element 2 prime. If that element is what we're looking for, terminate, right? Terminate DFS. We'll call that maybe 2A, right? And so, but what I was kind of just doing here, I wasn't really searching for any particular element. I was just kind of doing a traversal. And you notice that a search and a traversal are kind of the same thing in a graph, because you have to do a traversal in order to ensure that you see every element at least once, and then if that element's the thing you're looking for, then you stop. So a traversal is basically like a full search where you just don't find what you're looking for. It's like if you're searching for an element F, right? If we're looking for F, you would do a full traversal because you would look through the whole graph. Okay, so let's look at some other types of graphs and just think about what DFS is going to do on this type of graph. So let's say that we have 2 copies of this, except this is, say, E, F, G, H, right? And there's no boundary, or there's no edges that take you from A to any of these, or B to any of these, or basically what we would call this is well, there's a lot of words for it. I think the first word that I would use to describe this is disconnected, right? And normally what you would say is this is a graph with 2 connected components, right? Because a component in a graph is just as the maximal part that is connected. So the component of A is just this whole part here. The component of B is actually equal to the component of A, etc., etc. The component here is the same thing over here, or I shouldn't say it's the same thing. It's the same shape, but it's just a different component because these are all different vertices. So these are just 2 different graphs, and of course you could say, well, maybe, do they have to be clones? The answer is obviously they do not have to be clones or anything. We can make something where this is like, different. Something like Something like that you can make, no problem. So right now this is not drawn as a planar graph, so but anyway, the point is that these, if there's not a node here, let me just say that if you look at this, like, this, what would you call this? You would call this an intersection, right, of two lines, but it's fictional, right? And the reason why it's fictional is because intersections can only actually occur at vertices, right? So that vertex, there's no vertex there. So there's no way to go from, like, well, there is a way to go from F to G, but there's no way to traverse this path here and then, like, take a detour and go up to G. Whenever you see a line crossing another line in graph theory, if there's not a vertex at that position or some kind of dot that indicates that those lines are connected, then just assume that they're not connected. So that's one thing to think about. Okay, so cool. And so this is a graph with two connected components, and you can have a graph with a whole bunch of different connected components. But the thing is, like, basically, if we search, right, starting at A and we search for F, the answer is going to be nope, right? It's going to be false, right? We don't find it. And the reason is because you see that none of the edges actually get you to F, right? So it's possible that you can traverse a graph starting at a particular node and still not reach everything in the graph. So that's something you have to really consider. And that's part of what a graph search is. So basically, whatever you encode as a graph, for instance, like if this is two sets of aircraft routes, right? And you say, like, oh, I can fly from Albuquerque to Chicago, from there to Boston, from there to Dallas. What's Frankfurt? What's a G? I guess we could just say Hamilton and Bermuda. You know, I don't know. What starts with J? I don't even know. There's a whole, so there's a lot of different... The point is that if there's no flights that take you from, say, Albuquerque to Frankfurt, then that's why there's no edge here, right? And also there's no flights. Let's say that there's just no international flights or whatever. So, like, there's no flight that takes you from Albuquerque to Chicago to Frankfurt or any of these going into any of these. So that's basically the moral of the story there. So, okay, cool. All right, so it's possible that the search will not actually return true, even if the F is in the graph, right? So F is in the graph, F is in the vertices, but there's no way to reach it from A. Okay, so let's do a little bit of a visualization thing. I think I have the visualization pulled up. Here's the visualization. And you notice that they have a set of visited nodes. And I've selected an undirected graph. Small graph. I'm not even going to talk about adjacency lists or matrix representations. Maybe I will towards the end of the class, but I probably, maybe I'll mention adjacency matrices. But, okay, so let's say that our start vertex is, say, 4. And let's run a depth first search. So this is, I mean, again, so you notice that we're not actually entering something to search for. We're just setting the start vertex. So the depth first search is, this is a depth first traversal, really. So let's run it and see what happens, right? So the first thing, and hopefully we can slow it down just a little bit, right? So here we're visiting 6, and then 6 is going to visit 1. I guess 1 is going to visit 0. And then what's going to happen next? 0 is going to visit 3, and 3 is going to visit 5. And so the question is, and so you kind of see, why is, you see, I think, if we step back for just a second, 3 tried to visit 1, right? But 1 is already visited, right? The only things that aren't visited are 5 and 7. So for instance here, this is part of the depth first search algorithm. So it tried to visit 1 and it couldn't because 1 is visited, so let's step forward. Now it's going to try to visit 5. We can go to 5 because it's not visited. We mark it, so now 5 has been visited. We try to go back to 1. No joy, right? So now you see the stack. The stack is 4, 2, 6, 1, 0, 3, 5. And we have one node that hasn't been visited yet, which is 7. Right? So what we're going to do here is we're going to say, okay, so vertex 3 already visited, so we're going to pop, right? Returning from recursive called DFS 5, right? So we're going to pop that off the stack. Returning from recursive called DFS 3, yep. Going to go all the way back, going back to 1, going back to 6, right? And then we're going to go back to 2. And finally, we're going to go back and we're going to say, wait, now we're all the way back at the start. We've popped our way all the way back to the top of the stack. Are there any other children that we haven't visited? So we've checked our child 2. That was the first thing we did. The next child that we haven't visited yet is 6, so it's going to look at that. Or I shouldn't say that. The next child that we haven't gone to from 4 is 6, right? That's explicitly what I mean. So it's going to try to look along this edge, and then it says, wait a second, 6 has already been visited through some other path, so we ignore it. And then finally, we find 7, and we can go to 7. And then at that point, we just go back, and that is it, right? Complete. And so you see that every time you do a search, you're going to have to initialize, right, all these visiteds to false. And then what you're going to have to do is, so let's do another graph. Let's see, what's a good graph? Let's keep going until a good graph is, sure, okay. And let's start at, say, the node 2. Doesn't like that. So 2 is going to try to visit 5, right? Mark that as visited. 5 is going to try to visit 1. Then it's going to try to visit back and probably going to go back to 2. Then it's going to go to 6, or 3 and then 6, right? Because I think it's just kind of going in order. So remember that there's not a specific order that's required. I think it's generally just that the, it's just going to whatever the lowest numerical value is first, which is fine. There's no reason not to do that. It's kind of random. So you see that we've gone from 2 to 5 to 1 to 0 to 3, and then we're going to try to go to maybe 5 again, but that's going to be visited, right? It's going to try to go to, it tries first to go to 0 because that's the lowest value. Then it's going to try to go to 5, that's visited. Then it's going to go to 7 because that hasn't been visited. Let's keep going. So then it's going to say, okay, I'm at 7, lowest value is 3. Nope. Yep. Right, go to 4. And I think the last node that hasn't been visited is, nope, okay, 4 hasn't been visited yet because we haven't marked it. Now it's marked. And so now we go to 6, and we mark it, and that's it, right? And then it's going to step back. So it's going to step back through the entire searching process. So it's going to go to 7, to 3, to 0, to 1, to 5, and then back to 2. And you see that it's not visiting any new nodes because everything's already marked, and we're done. Okay, cool. So before I do any implementation, I think I want to do some implementation, but before I get to that, let's talk about the other way to search through a graph. So we've talked about depth first search. And so you might be wondering, well, okay, you've been talking about BFS, which is breadth first search. And so what is that? And how is it different? And so I think the cool thing to think about is that for DFS, the important thing about DFS is that it's a stack, okay? Like, the algorithm itself is kind of a follow your nose thing. If you start with a stack and you basically do the common sense things, which is go to a node, visit its children if they haven't been visited, etc., then really you can, if I just told you that DFS relies on a stack, then, you know, with enough time, you should be able to figure out kind of the algorithm for depth first search. So for breadth first search, what I'm going to say is that instead of a stack, we use a queue. And actually, the algorithm is the same, right? I shouldn't say exactly the same because it's not 100% the same because, of course, you can't say push and pop. But the algorithm is basically, instead of this, you NQ and DQ, and here you would NQ, right? So you just change the words, right? So that's why I say the algorithm is the same. You NQ the starting element, you DQ op. Let's get rid of that. You DQ an element. If that element's what we're looking for, we terminate BFS. You mark that element as visited. You NQ the children if not marked, and then you do nothing if marked, and you go to 2. So that's exactly what that's how the breadth first search works. So instead of a stack, you use a queue. And so let's talk about how that's going to work on our little sample test graph here. Let's say that we're starting at A and we're doing a breadth first search for this. So the first thing we're going to do is we're going to NQ A, right? NQ A, and then of course you might say, well, that's pointless. We're just going to DQ A, but we have to start somewhere. So we're going to DQ A, and then we so is A what we're looking for? Let's say we're looking for F, right? Search for F, F or traverse all, right? So if we DQ A, then we're going to NQ B and C. So at this point, the queue was A. Now the queue is empty, right? And now the queue just has B and C in it. But actually, if we NQ B first, that's the cool part, because then B comes here. And so that's the queue now. And so what we're going to do now is we're going to say, okay, now we DQ B, and then we NQ, I guess, A, C, and D, but then you know the problems, right? So A has already been visited, so once we DQ A, we mark A. DQ B, we mark B. So A and B are now marked. So let's mark them. And so then in Q, we NQ A, C, and D. So basically the point is that we're not going to NQ A. So we don't do A since it's marked. But we can NQ C and D. So basically what we're going to get is now the Q is, we've DQ'd B. So actually the Q is going to be C, and then I guess we NQ A first. So we don't do that. And then we NQ C again, and then we'll NQ D. So that's what's going to happen, right? So we have DCC like this. And so what we're going to end up with next is we say, okay, DQ C, mark C, right? So once we do that, what we're going to see is that, or what we're going to visualize, is that C gets marked. And now we're going to push on the children. So we're going to NQ A, B, and D. But A, B, and B are already marked, so no, right? They're already marked. So the only one left to NQ is D. So actually, what we're going to end up with is we're going to end up with D, D, C, like that, in our queue. And so now the point is that since our queue is D, D, C, what we're going to, because C was in queue twice, what we're going to do is remove, like, we see that C pops out, so we're going to DQ C again. But it's already marked. So now we're going to DQ D, not marked. So when D is not marked, what we're going to do is mark D. And so then we'll DQ D again, mark D. And then how do you know this algorithm? So this is a good question. And it's the same question as for BFS and DFS, is how do you know that these algorithms have terminated, right? How do you know we're done? And the answer to that question is actually, you know that you're done when the stack or queue is empty. Now, of course, you might say, well, the queue is actually empty once I inQA and then DQA. But let's be more specific. When the queue is empty after pushing or after inqueuing, right? All of the children, right? And so we don't talk about it right as we DQ, because it's possible that after we DQ, especially in the first graph, so it's always possible that as we DQ the first time, we're going to find out that the queue is empty. But then remember that we're still in this is still one step here. So a DQ, mark, NQ, right? That's the next step. So something like that. So basically the point is that each of these steps, when you do these steps like this, and then these are each steps on their own, I guess D is already marked, so the answer is terminate. Queue empty. Right? So the queue is empty, so we terminate. Or the stack is empty, so we terminate. And so the good news is that there's actually a way, and we're guaranteed as long as the graph is finite, right? So, in mathematics we can talk about infinite graphs all the time, but in computer science, you can't really talk about an infinite graph, mainly because an infinite graph would require probably infinite memory to store if it's just some kind of general graph. I mean, you could come up with some formula for the edges or something like that and maybe do something like that, but the point is that, unless you're really tricky, right? So an infinite graph would require infinite memory to store. So as long as the graph is finite, eventually these algorithms will terminate, which is great, right? And so, why are we so interested? And we'll talk, if you take algorithms with me, we'll talk a bit more about this, but why are we always so interested in whether algorithms will terminate? The answer is basically, I think it's actually a pretty simple question to answer why we care. Why do we care if algorithms terminate? And the answer is because otherwise it's an infinite loop, right? Or recursion, or some kind of horrible thing, and you'll never, you'll wait forever for the answer, right? Basically, there's a lot of algorithms out there that they're called, at least in mathematics, they're called recursively enumerable. So and I know that that's a silly, it's a crazy term. It makes no sense in computer science, but what it means is that there's an algorithm exist which basically they're algorithms which produce true or false, and sometimes and the thing is that if it's going to produce true, will happen in some finite time, right? But if it's going to produce false, the answer is that actually it will never. So it's not always. It can either terminate or produce, or I'm sorry, either terminate in false or just not terminate. Okay, and so that's the problem with recursively enumerable algorithms, is that they're basically a list of instructions which, if the program works, it finishes, but if the program doesn't work, it's possible that, or I should say, if the program works, it terminates in true or false. But it's also possible that it may just never terminate, right? And so that's that's something that's very dangerous, obviously. You don't want to live in a world where like half of your computing algorithms have this, hidden time bomb where, yeah, maybe they'll just not terminate and maybe they'll just explode on you and you'll just wait infinitely long for the answer. So, okay. All right, so basically the moral of the story here is, and this is really all you have to learn, I think. You have to learn this algorithm, but I think the algorithm it's kind of what's the obvious thing, right? The hard thing to remember is that depth first search always takes a stack, and breadth first search takes a Q. Okay, and that's it. So, let's see if we can implement a DFS or a BFS in C++ in a half hour. So let's do something like that. So let's make a graph class, right? And so what kind of things do we need for a graph? And I'm going to be lazy here and use the std thing. So first thing is we need a struct, which is going to be a graph node. Same business as always, right? The graph node is going to be some kind of thing where we're going to have say, let's actually use strings. So we say include string, right? And so what we're going to do is we're going to have, what am I doing? Right, maybe reference, and then we'll say, this should be, at this point, this should be old hat, right? This is not surprising stuff, I don't think, right? And so basically here, what we're going to do, and you know what, maybe we'll add let's not add the visited to that just because, well, actually, you know what, let's do it. No reason not to. So you might be like, but, it's a waste of a byte. And so let's make mName, set that to name, visited, set that to, okay, I'm jumping too much. Set visited to false. Sorry, I keep hitting page up and down. Okay, cool. So that's really all we need for the structure of a graph node. And so now what we're going to do, so let's have a graph. We need a graph constructor. What else do we need? Maybe let's just do depth first search. And we'll have search for element, so string element to search for. And we'll make this a Boolean, right? And then we'll do a Boolean breadth first search. Make all this public. What else do we need to do? So we need to make some private data elements. So private. What we'll have is a vector of graph node. Well, actually, we can even just, yeah. Let's do it up simpler. Graph node pointer. Okay, and then we'll have an int number of elements. So the size of the graph, and maybe we'll take the size of the graph here, and then we'll have some kind of display function, which will display the graph. And of course, we're not going to be able to draw it out in a nice, pretty way, unfortunately. Not this fast, right? If you're looking for pretty visualizations, then go to the visualization website. But here, what we're going to do is something like this, and so then maybe we'll have a create random graph, right? So okay. So let's think about this. So what are we going to do now? Let's do this. Let's put some graph colons, right? There we go. There we go. Get rid of private. There we go. Okay. So the first thing we'll do is set mSize equal to size. And then what we'll do is create a random graph. And so I just want to create a random graph. You'll see why I want to, well, because I don't want to actually have to program in the graphs. I mean, it's possible that, you know, we might be able to do something that's less intrusive than just creating a random one. But yeah, so how do we make a random graph? So the first thing is we are going to, we're going to say, what is it? M, or what is it? Graph nodes. Graph list equals new graph node mSize, like that. Why don't you like me? What's the problem? No matching constructor for initialization of graph node. Interesting. What have I done wrong? Oh, you need to. Good question. How do we do that? I mean, I guess we could make them graph node pointers, but that's not good. Well, you know what? We can simplify. Okay, even better. What we're going to do is just get rid of this so that we don't have to do that. We can just set the... Okay, cool. All right, so how do we create a random graph? So the answer is going to be that we have to give all the graph elements names. Maybe instead of creating the random graph first, we'll just actually do the search first. That way we'll at least do the correct thing. So let's do it this way. So let's say for, so remember what we're going to do here, right? The first thing we're going to do is we're going to have a stack. And I think we can actually just use the STL stack, right? So let's include the stack, right? I think you can just include stack. And then from the stack, what we can do, let's make a stack. So it's lowercase, unfortunately. Okay. And then what we're going to do is, I guess, I guess we actually have to search through. So it's kind of pointless because we're looking through every single node to find the element, but whatever. So this is not really part of the algorithm. So what we're going to do is for, say, graph node children. Did I make it m children or something? What did I do? Oh no, okay. It's we have to do it the regular way. So let's say if element is equal to pgraph list at I dot name, right? Then what we're going to do is we have to assume that the names are unique. we'll say DFS stack dot push, and we will push back the first thing. So this is not really part of the algorithm. This is just finding it based on the string. And this is kind of bad because it's already an O of n or O of v, where v is the, I guess it's not O of e, so that's fine. Anyway, so now the algorithm actually starts, right? So what we're going to do here is we're going to do something like, well, let's get the current node, so graph node pointer p current. And so what we'll do is say while DFS stack is, let's see, empty, right? While not DFS stack dot empty. Cool. And so what we're going to do is we're going to say current is equal to DFS stack dot pop, right? Why does it not like me? Cannot, hang on. Thought we were doing pointers here, so it should be fine. Cannot initialize a graph node pointer with an R value of type void. Huh. Weird. Because I specified that it's a graph node pointer. It shouldn't be type void. Unless pop doesn't actually, is it like a dot get? Dot. No, it should be pop. Oh no, top. Okay. I got it. So their stack is implemented a little differently. So this gets the top of the stack, and then we do a DFS stack dot pop, which returns void. There we go. So they have a top and a pop. Okay. See, I always forget this stuff, but it's been a long time since I've actually used the STL stack. But anyway, so here's what we do. So we'll just follow the algorithm, right? So we say if the p current, right, is visited, or let's say if not visited, right, then what we'll do is we'll go through the children. We'll say for p current right, we'll go through the children, and we'll say if child, right, visited. So if the child isn't visited, then we'll push it onto the stack. So DFS stack dot push child, right? There we go. So, and that's really it, right? And then of course the thing is here, if the thing is visited, then so if it's not visited, then we should mark p current visited equals true, right? So we have to mark it, we pop it, we mark it, we push the children, and then what we'll do is we'll say if the thing is equal to the element, so I mean, I guess actually what we need is a start. Let's say start and find. That way we'll have two elements. So let's change that. Okay. So, all right. So then we'll change this to start, and then we're actually looking for find. So let's say if we find the element find, then we return true. So basically, if child dot and name is equal to find, we can return true, right? And then the thing is that if this whole algorithm finishes without finding anything, then we return false, right? Because it never found it. And as it turns out, this is basically DFS, right? This is all it is, right? So you have while the stack isn't empty. Now this is two lines, whereas I'm saying we pop, but in my mind, pop should return the element. So if I ever implemented a stack, pop would also return the element. Here they have an element top and an element, or a method top and a method pop, which I think is a little bit stupid, but whatever. What are you going to do? Oh, I think I know why they do it that way. They do it that way because they don't really know. Remember, if you're going to pop something off the stack, it could very well destroy that thing, right? Like call its destructor. And so you don't want to have it call its destructor if you're just going to look at it. I think that might be it. You want to have the end programmer save the object before they pop it. And that might be their excuse for that. Really, pop should always return the element. I'm not 100% sure why they've implemented it that way. But anyway, so you check if the current thing has been visited, just for safety. If it hasn't, you set it's visited to true, and then you go through all the children, and then you push them onto the stack. So the cool thing is that DFS and BFS are going to be very similar, right? Because all you have to do right, so all you have to do to change this let's change this into a breadth first search. Right, so let's copy and paste. And okay, so the first thing we have to do is we have to change the signature of the function, right? I have to change it to this, and we have to change it here, right? Yeah, so let's think about it this way. So what do we need now? Let's hope that there's a queue, right? Let's include queue, right? And then what we're going to do is let's create, instead of a DFS stack, let's make a queue. And let's just call it BFS queue. And so here we'll do BFS queue.enqueue. Hopefully that's a method. It is not, so let's see what the methods are. Oh, are they just using push and pop? Yes, they are. So we can actually just, in this case, push is equal to enqueue, right? And so we change DFS stack to BFS queue, right? A little bit of copy paste business. Technically, there's smarter ways to do it, but whatever. And so as it turns out, the only difference is that this is front instead of top. But other than that, this has now changed. So depth first search and breadth first search are basically, as I say, they're the same algorithm. The only difference is that you replace the stack with a queue, and instead of pushing you enqueue, instead of popping you dequeue. The nice thing about the STL one, apparently, is that they use the same thing for push and pop. The only difference is that top becomes front, right? Front instead of top, right? And that's it. Okay, cool. So let's see if we can actually get this working. We have 15 minutes left in class. So it's possible we can get this working. So let's see if we can do it, right? Let's create the display method first. So the display method, and then I think we're gonna wanna do some couting. So let's include IOStream, just so that we can see what we're doing, right? We want some output. Let's say for int I equals 0, I is less than size, I plus plus, right? Okay. So I think, what's a good way of displaying all this information? The thing is that we kind of have to display it. We're going to display it as something called an adjacency list. And so what an adjacency list is you have a list of your nodes, and you display just the connected edges. So for instance here, let's say cout p graph list at I m name, and then p, let's put in, say, colon connected to and then we can do for something like this. Oh yeah, and these are dot pointers, so it's just dot, and then we do child dot. And then at the very end, we cout. But that's that. Okay, so that should be our display method. That took 2 minutes, so we have 13 minutes left. So basically, I'm just terrified of making this. I've been really avoiding this function, clearly, right? Creating a random graph. Yeah, I've definitely been avoiding it. So let's not avoid it anymore. Let's do it. It's the problem is that it's not actually a graph algorithm. It's not like a standard graph algorithm. This is just something that we're going to make up in order to create a graph, right? So I think we want to include random. That's not how you include random. That's how you include random. So so now let's think. Basically, we have a size, right? So the size is already fixed, and we've already created our graph nodes. So the first thing we need to do is give them names, right? It's a bit annoying, right? So the first thing we have to do is give them names, and then what we have to do is connect them randomly to each other. So let's see what happens. And I just remembered something. We have to, whenever we do the depth first search or breadth first search, while we're going through here, we also have to set all of these things not visited equals false, because they might have been set to true on the previous run, right? So if we have multiple runs, we have to set basically all of this stuff to false, and we don't want that in the if statement. We just want it here inside the for loop. Yep. So now that I remember to do that, because otherwise the problem is that if we don't reset everything to false every time, then it's going to start with the idea that some of the nodes have already been visited, and then it won't work properly. So let's give them names. I don't know. How do we generate random string? Okay. I'm gonna be even dumber and just copy paste some. I'm not even sure if it's the best code ever. It's literally just what we're gonna copy paste. And let's not use any numbers or uppercase. Let's just use srand, so I guess it wants us to use, what, ctime? And something like that. Okay. I don't have that. Does this work anyway? Okay. That should be fine. I think this should work. What's the problem? Use the C++ random library instead. What is it? Has limited randomness. We really don't care. We're not very interested in exactly how random it is. So the first thing we're going to do is we're going to say for I equals 0, I is less than m size I plus plus, like this. So the first thing we're going to do is go p graph list I dot mname equals generate random, and let's make the list the length 5. It's just going to be 5 random things. Hopefully it won't generate anything that's already been used. I guess that's actually a danger. But I don't think we're using the names for anything. The names are just being used for display. So, and hopefully there won't be, let's make the names like 3. So, okay. And now we have to connect them randomly, right? So what we're going to do is we're going to say, well, okay, for int j equals 0, j is less than m size j plus plus. If j is not equal to I, and what's the other kind of thing that we want to check? Maybe some random condition is true, so rand mod 2, right? So that's giving us a 50-50 chance of connecting any two nodes. I guess we can start with that and just see what happens. Then what we're going to do is we're going to say, oh, I know. That'll fix that. So now we only have, okay. Yeah, let's just leave it as 50%. So okay, that's good enough to start. If this works, then we can modify the probabilities and be smarter about everything. But so what we're going to do here is we're going to say p graph list, and we're going to make this an undirected graph. So the graph at I dot children dot push back, and we're going to push back the thing at j, and then we're going to do the same thing with I and j flipped. So the thing at j, we're going to push back the node at I, and so now that connects it in both ways, right? So this is basically adding ij to the edges, and this is adding ji to the edges. So that makes it undirected, right? Okay, so are we done? I think that might be it. So now we just have to make like a driver program for this thing. So let's make a driver program. All right, so the first thing we do is, because this is the same project as the disjoint union stuff, we just say void disjoint driver, and we put that code in there. And then actually we copy paste that code because we're lazy, and we call this the graph driver. And so we run the graph driver like this. And so what we're going to do is we're going to create a graph. So let's include our graph, right? That G, let's make it size 10 just to start with. So what are the things we can do? So the things we're going to be able to do are DFS, and these also need to be strings. So G dot depth for search, and what we're going to do is search starting at X going to Y, and then we'll see out if this, we'll see out found, else cout not found. Right, and then we'll do the same thing with breadth first search, and we'll do this, and then this will be g.display. So I think we're almost there, right? The only thing we have to do, so we did the constructor, we created the thing. I think we're good to go. I mean, of course, it's probably going to explode, right? Because I haven't done any testing. This is going to explode, right? Almost certainly. Oh, illegal indirection. Illegal plus for class. Main dot. Oh, type what the. Okay. Now that that is gone, let us try again. Okay, so I want to display the thing and just see what we got. Oh, interesting. That's stupid. The same. Because. That's only 10% my fault. Okay, that's only 10% my fault. Mostly that's their fault, okay? They put their seed in their random generation algorithm, which you don't want to do. You only want to run your seed once. Okay, let's try this again. I didn't think about it at the time. Okay. There we are. So now we have XQL that's connected to these ones, right? So now let's DFS starting at XQL, and let's go and try to find LHI. Okay? And let's see what happens. Okay, so it found it. So that's not very entertaining. So let's boost up our DFS and every time it goes to a node, let's print it out, right? So this is, you don't really want to be doing this in general. You know, this is going to absolutely destroy your this is going to destroy your runtime to have all these print statements happening, but we don't care because we only have 10 nodes, right? So, okay, and let's put this here. All right. Maybe we can even, if we're really creative, we can even output the stack. So let's see here. So let's display so that we can see the names of the nodes. Now let's say DFS reg to I don't know, reg to bro. Oh no, bro is just connected to it. That's boring. Let's go to ZCQ. So the first thing it did was it went to reg. Oh, and ZCQ is connected, so that's stupid as well. DFS from reg to, or let's go FTW, right? And what is it not connected to? It's not connected to bro. So the first thing it did was it decided it was going to go, it visited FTW, and then what it did was it looked at the children. I guess it pushed the children like this, so if it's pushing them onto the stack, it's pushing them like this, right? So this one's at the top of the stack. And then UHL is connected to a whole bunch of these nodes. So actually, let's make the probability lower that these things are connected. Let's reduce the probability to say 1/3. So we can reduce the probability to any 1/n by just doing this trick. It's like a, wait, where is it? Where's my create? Here it is. Let's reduce the probability, because unfortunately the graph is too connected. Everything is too connected, so that's bad. So now let's display. Whoa. Now I'm really confused. Oh, we want to... I made the probability 2/3, not 1/3. There we go. Reduce the probability, not increase the probability. So let's display the new graph. So, okay, so that's good because everything's connected to like 2, maybe 3, maybe 4 things. We're not getting quite as big of connected lists. So now let's BFS from HBA to something. I don't know what's not connected to HBA. Let's search for DXO. Okay, well that was connected. DFS. Let's go to IQF. So here what it had to do to breadth first search was it went, what was the path that it took? So it looked at this one, and then 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 it looked at this one. And then I guess let's see, where is IQF? Is it connected to TFB? Nope. DXO? Nope. DNW? Here it is. I see. So what it did was it looked through all of these, right? And so what it did was it visited here, it visited here, it visited here, it visited here. And then one of the children of DNW was IQF, so it found it. All right. So that's basically how these DFS and BFS work. All right, so let's quit out of this. That's really all we have for today. Maybe not the best naming of nodes, maybe not the best connected graphs, but what do you expect? I had to do it, I had 15 minutes to come up with this, so that's what I did. All right. The only thing that... Oh, no, I'm sorry. I was a little confused. I was like, wait a second. HBA is connected to this, but this isn't connected to that. But they are. Yep, everything is connected. Everything works. So I think the more interesting thing to do would be to make the graph larger and to have connected components where you wouldn't necessarily have everything connected to everything else, and to look at that kind of stuff. All right. I think that's, as I say, that's all for today. I think we will, so next class will be our last class, and so that's going to be, we're going to talk about what we've done this semester. We're going to do a review. I'm basically going to go through everything, and if you have any questions, you can ask, and that's basically it. All right. Cool.